In this video, I'm going to answer a couple of questions that were posed to me by students who are wondering how you get to a specific answer. So our first question shows up on here, question 5. So this question was asked, and it says the species that will oxidize chromium-2. And so they've given us 7 species. Chromium-2 is in the data booklet, but this is oxidizing, so we want Leo, right? So what chemicals will cause chromium-2 to Leo? So we're going to refer to our data booklet, and we need to find chromium-2, and chromium-2 is on both sides. So the challenge in this question is, do you recognize that this chromium-2 is the one we're talking about and not this chromium-2? Because the chromium-2 on this side is Leo, Ra. So the chromium-2, it needs to be chemicals that are up here that are going to react with the chromium-2. And so the chemicals that are going to be listed there include fluorine is one of them, but aluminum isn't, right? Aluminum is down here, and it would spontaneously react with this, but in this case, it's not causing chromium-2 to be oxidized, it would cause chromium-2 to be reduced. So it would not include aluminum, but silver iodide is in here. I believe silver, where is silver iodide? Silver iodide is at negative 0.15, so it's here. So that's one of the options that would work. Water wouldn't. Water is down here, so it won't work. But an iron 2 wouldn't work because iron 2 is below it. But nickel 2 would work, and so would oxygen and water. So those are going to be our answers for that question. So we're going to get 2, 3, 6, and 7 are going to be answers for that. And we also had a question about, on question 4, or on page 4, there was a question about question 11 here. And so it says, match the species numbered above with the descriptors given below. So we've got the species here, and they've given us a reduction half reaction table. Now, this table has been set up for you, and it's kind of easy to spot because you can see that the voltages are going from highest to lowest, most positive to lowest. So this is going to be our strongest oxidizing agent. This will be our weakest oxidizing agent. Our strongest reducing agent will be down here, and our weakest reducing agent will be down here. So it says species that will react spontaneously with TL positives. So the only chemical that will react spontaneously with TL positive is americium-4. A reducing agent that will not react spontaneously with chlorine. So now this part of the question is something I need to reference the data booklet for. So chlorine, if I look for chlorine up here, chlorine is at positive 1.36. So if I come back to here, chlorine fits in here. So I get Cl2 goes here, and we get 2 chlorides plus 2 electrons. And so if I did that, the only chemical that will not spontaneously react with chlorine is americium-3. So that's going to be 5. That's the reducing agent that won't react with it. The reducing agent that is stronger than calcium. So again, I need to reference the data table, and calcium is down here. Calcium is negative 2.87 volts. And so calcium Ca2 positive plus 2 electrons is calcium. And this says a reducing agent that is stronger than calcium. Well, it's my strongest reducing agent. It's cesium. So 8 is the answer there. An oxidizing agent that is stronger than permanganate and the acid particles. Permanganate and the acid particles are positive 1.51. So the strongest oxidizing agent here is actually stronger than it. So it's the americium again. So that's how you would handle that question. And sort of what you need to be able to do is recognize that these voltages line up with our own data table. There's a question 6 on, or a question on page 6. On page 6, it was question 4. So that somebody asked about. Oh, sorry. Here, and it said that there wasn't a reaction for it, I think, but it doesn't matter what the reaction is. The reaction, they're asking in this question what the oxidizing numbers for the metal in each of these are. So my sodium ion is like this. So it's going to be a +1. Sodium here is 0 because it's an element. Iron is 0. And in the last one, this is an iron 3 oxide because there are 3 oxides. So this is +3. So there wasn't, the reaction wasn't given to you, but you didn't actually need it to be able to do that question. And then there was another question on page 9 that was asked. Just give me a second. Let me see which question that was. Oh, sorry. Question 9 on page 7. Oh, sorry. This was a question that was asked. It's on page 7. Question nine on page 7. I think my pages are screwed up here. This is the question that was being asked about. So this question says the statements that apply to this titration. So it's referring to this titration here. And we need to read through what's going on in this. So essentially, they've got iodine. So the concentration of vitamin C in a sample of grapefruit juice can be measured by titration with an aqueous iodine solution using starch as an indicator. When unreacted iodine is present, the starch forms a purple complex. The titration reaction is represented by the following reaction. So in the experiment to determine the vitamin C concentration in grapefruit juice, a student titrates 10 milliliter samples of grapefruit juice, so that's their sample, with a 0.1 mole per liter solution of iodine. This student records the following data. So it says here, statements that apply to the titration. So the indicator changes color at the end point. The grapefruit juice should be placed in the burette. Well, it says that the vitamin C, so they have 10 milliliter samples of grapefruit juice. So the grapefruit juice is not in the burette. The grapefruit juice is in the sample because it's the 10 milliliter volume. The sample should be measured with a volumetric pipette. The sample should be measured with a graduated cylinder. The iodine undergoes reduction. So here, my iodine goes from 0 to -1. So that's GR. So it's not reduction. The iodine undergoes disproportionation. That is not correct, right? It's not disproportionation. The iodine would need to both gain and lose electrons. It is not. So I've got other things. The indicator changes color at the end point. That occurs in titrations. And the iodine, does undergo reduction. So I think my answer is going to be 1, 3, 4, 6. Okay, and then, So there was a question about on page 15, which is numeric response on page 15. And that's an important question. This one says the statements that apply to both voltaic cells and electrolytic cells. So there's a table in your notes about, or in a video, and is also in the notes, but it's important to know the difference between electrolytic and voltaic cells. And so there's a table in here that shows the differences and similarities between them. Sorry, it's shown here. And you need to know the similarities and differences between the electrolytic cells and voltaic cells. So getting back to our question, it says the statements that apply to both voltaic and electrolytic cells. So the net potential is not going to be positive or negative for both voltaic and electrolytic. Voltaics are going to be positive, electrolytics are going to be negative. Reduction occurs at the cathode. That is true for all cells. GR-OAC, so that applies to both. Cations travel towards the cathode. That applies to both. Electrons travel towards the cathode. That's where they're gained. The electrons are gained. And the flow of electrons is spontaneously generated. Spontaneously generated is only for voltaics. So voltaics are spont, electrolytics are non-spont. So that's not true. And the strongest oxidizing agent reacts at the cathode, and that is true. I think that that's almost all the questions. There is a calculation question for the methanol fuel cell. This question does not have enough information. The information that's missing from it is here. So you need this information from the very start of the test to be able to answer that methanol fuel cell question. Hope this helps.